Welcome to the first substantial video in the group theory series. In this video, we will introduce number groups. To begin with, we start with the example of the integers denoted by this double struct z, which is equal to 0, 1, 2, and so on, together with all of their negatives, so also -1, -2, and so on. So why is this a group? Well, it's not until we specify an operation anyway. We'll use the familiar operation of addition. In order for the integers with addition to be a group, the operation must be what we call closed. What closure means is that if you take two things from the set and perform the operation, then the result of the operation is already in the set. So in the context of the integers, this means that if you take two integers and add them, you get an integer. We will take this as a basic fact and not prove it. Note, it is possible to prove this fact from the axioms of set theory, but such a proof is more appropriate in the context of a course on set theory. So we will take this for granted. It's worth seeing an example of an operation that is not closed so that you can see how this property sometimes fails. For example, sticking to the set of integers, if we merely equip this set with the operation of division rather than addition, then the operation is not closed because 1 is an integer and 2 is an integer, but 1 divided by 2 is not an integer. The next property required of a group is associativity. This is the property that any parenthesization gives the same value. For instance, in 1 plus 2 plus 3, there are two parenthesizations, 1 plus and then paren 2 plus 3 close paren, and paren 1 plus 2 close paren plus 3. Each of these results in 6. The fact that this always works out for any integers is the associativity of integer addition. Again, it's good to see an example where this fails. Take, for instance, the integers with subtraction. The expression 1 minus 2 minus 3 has parenthesizations, 1 minus paren 2 minus 3 close paren, and paren 1 minus 2 close paren minus 3. The former evaluates to 1 minus -1, which is 2, and the latter to -1 minus 3, which is -4. Since these are unequal, subtraction is not associative. The next property that any group must have is to contain an identity element. For the integers with addition, the identity element will be 0 because 0 plus x equals x for any integer x. More generally, an identity E is an element that leaves every x alone. That is to say, EX equals x, or you could also do E plus x equals x, or you could do x plus E equals x. Either way should be fine for every x in the set. Okay, then the last property that a group must have is for it to have all inverses, or to be closed under inverses. If x is any integer, its additive inverse is -x. This is because x and -x always combine to the identity. That is to say, x plus -x is equal to 0. For a concrete example, the additive inverse of 1 is -1 because 1 plus -1 is 0. Also, the additive inverse of -1 is 1 because of the same equation. We could repeat everything we just said for the integers, this time for the rationals or the reals or the complex numbers. However, with the rationals, there is a slightly more interesting conversation we could have for demonstrating its closure under addition. Note the very formal and technical definition of a rational number. Q is a rational if and only if there exist these integers R and S such that S is not 0 and Q is R over S. To show closure, we select two numbers, A over B and C over D, satisfying these conditions, and prove that A over B plus C over D also satisfies these conditions so that it is a rational number. By definition, A over B plus C over D means AD plus BC over BD. And notice that that is just the same thing if you did the standard procedure for adding rational numbers together. You would multiply the top and bottom of the A over B. You would multiply that by D to get common denominator. You would go over to C over D, multiply top and bottom by B, and then you would have common denominator, and then this is what you would get for their sum. Okay. Now, AD and BC are both integers by the closure of integers under multiplication. Then AD plus BC is an integer by the closure of integers under addition. Also notice that BD is an integer, again, by the closure of multiplication of integers. Now, further, we know that B is not 0 and D is not 0 by assumption, and therefore their product cannot be 0. And that is all that we then need to establish that by definition, this AD plus BC over BD is a rational number, and that concludes the proof for closure under addition. Now, we could likewise prove associativity, identity, and inverses. However, I find these proofs not especially helpful for understanding group theory, so I will skip them. Let's move on to talking briefly about the integers mod n for any natural number n which is strictly greater than 1. Just for demonstration purposes, let's take n equal to 5. One way to think about this is to define x mod 5 for any integer x to be the remainder after dividing x by 5. So for example, 0 mod 5 is equal to 0, 1 mod 5 is equal to 1, and so on. We can eventually get down to 5 mod 5, which is equal to 0, and 6 mod 5, which is 1. By the way, note that you can also do this for negative integers. Negative 1 mod 5 is equal to 4. That's because when finding the remainder of a number after division by 5, what we want is to find a quotient q, which is some integer, and a remainder, also an integer, such that x equals 5q plus r. Now, if x is 6, then what that means is we take q equal to 1 and r equal to 1, because with those choices of q and r plugged in, we get 6. We always want the remainder to be between 0 and 5. So if we now apply this to the case of negative 1, then it's clear that we're going to have to take q equal to negative 1, and then we require that r is equal to 4. At this stage, though, we actually don't want to consider all integers. Rather, in order to talk about the group Z mod n, we require that z mod n is just equal to the set of 0, 1, and so on up to n minus 1. Then we can say that addition of two integers x, y in the integers mod n is defined by x plus y mod n. For instance, in z mod 5. For 3 and 4 in z mod 5, we take 3 plus 4 to be 7 mod 5, which is 2. This way, our operation will be closed because the result of the combination will be in the set 0 through 4. But because we always take our elements to be in z mod 5, which is 0 through 4, then we should be careful about additive inverses. Take, for instance, the additive inverse of 3 in z mod 5. We might write negative 3, but we must keep in mind that negative 3 is in z mod 5, and therefore negative 3 is really just notation for that element x in z mod 5, such that x plus 3 is 0, the identity. Which element could that be? Well, because 3 plus 2 is 5 mod 5, which is 0. And keep in mind that 0 is still our identity element in this group. This shows that negative 3 is actually 2 in z mod 5. What about other operations on number sets? We've already seen that subtraction fails associativity, and division does as well. You should check division for yourself. What about multiplication? Turns out the answer is no. Why? Well, it's not for failing closure. No matter which number set you pick, whether it's the integers, rationals, reals, or complex numbers, the product of two numbers is again a number in that set. Is it because multiplication fails associativity? No. Multiplication is associative for each number set. Identity? No, there is an identity. The multiplicative identity is 1, because 1 times x is equal to x for every x in the set, no matter which number set you pick. So it must be inverses. And indeed, this is the property that multiplication fails for every number set because every number set has 0. There is never a multiplicative inverse of 0, i.e. there is no number x in any number set, this double struck x, which could be the integers, rationals, reals, or complex, such that 0 times x is equal to 1, which is what we need for an inverse, a multiplicative inverse. By the way, this is the same as the fact that you can't divide by 0. Now, all of this naturally provokes the question, what if we just got rid of 0? For some number sets, it turns out this actually does turn them into a group under multiplication. For instance, this works for the rationals, reals, and complex numbers. However, for the integers, this does not suffice. And that's because also 2 is an integer, and there is no integer x such that 2x equals 1. Okay, what about for the integers mod n? Well, this is more complicated. For n equal to 2 or 3 or 5, 7 or 11, and so on, the answer is yes. However, for n equal to 4, 6, 8, 9, and so on, the answer is no. Just to give one demonstration, in Z mod 4, 2 has no inverse. And we can see this by a brute force enumerating of all products in Z mod 4 removing 0. So 2 times 1 is 2, 2 times 2 is 4, which is congruent to 0 mod 4. 2 times 3 is 6, which is congruent to 2. None of them turned into the identity. More on this suspicious pattern in the n's for which Z mod n removing 0 is a group under multiplication later.